All right. So firstly, thanks so much for the opportunity to present here. Thank the organizer for kindly giving me a slot to present my work. And it's also a very nice privilege too for someone working in this field to have, several guys who I have been reading papers as well as a graduate students being here in the audience in the same room. So, Bob, Ariel, and Victor should be here at some point. Yeah, so this work is on dynamic games estimation with Abhimanyu Gupta, Leonardo Pupi, and Fabio Sanches. So the overview on what we do here is we propose a new estimator for a dynamic decision problems and dynamic games with time-varying unobserved heterogeneity. So what I'm trying to say as the key features of our estimator is that it's easy to compute relative to some benchmark estimators, and we do not rely on the use of instruments or finite dependence assumptions. And the main idea is rather simple. So we actually attack the estimation problem, in my view, rather directly, where we just import, we do k-means clustering on the CCP. And after you do that, then you just continue with a standard two-step estimation procedure. And of course, some econometric theory to do for this. So in this sense, I guess this particular talk is a little bit different to some of the some talks we had this morning. Anyway, so in this talk, I would focus on the presentation of a single agent model. But then the paper is written intended to be applicable to games, and then the simulation studies that I will present would be done on games as well. Okay, so in terms of the model that we look at is really we directly build on the classic RUS dynamic discrete choice model and the first generation of dynamic games paper that built on RUS model. So in this setting, we know that there are many two-step estimation procedures available if there's no unobserved heterogeneity, right? And the typical motivation for using two-step estimation method is to reduce the computational burden. And this is particularly useful in dynamic game setting, especially if you're willing to digest the assumption that the data that you observe comes from a single equilibrium, because when you estimate games, then you don't need to worry about multiple equilibria if you're happy with that assumption. So keep on looking at Ariel when I say, if you're happy with the assumption that the data comes from a single equilibrium. Yep. So yeah, then there's of course a concern that the model might have unobserved heterogeneity, and how do we account for that, especially with the two-step estimation procedures. So often we see that the unobserved heterogeneity in this class of models come in the form of time invariant variables. So what I'm going to do in this talk is we're going to have time varying unobserved heterogeneity, and this can be motivated by unobserved macro or market factors. So along this line, the main benchmarks that we are comparing ourselves against are the procedures by Arcidiacono and Miller and Kolupstidi et al. So I mean, Hu and Sham also, they study the identification of this class of models too. But I think they, as typical of Ying Yao's paper, you kind of make assumptions and then you apply the misclassification stuff. And I think I don't think that's the direct approach that is comparable to the other papers. And I think it's perhaps less natural for empirical researchers to use them. Okay, so focusing on Arcidiacono and Miller first. So if you had attended the summer school, you have seen this, of course. And that paper proposes one uses the EM algorithm to estimate these dynamic models. And that paper allows for a more general form of unobserved heterogeneity than what we are concentrating on. Okay, so we're just going to focus on the time varying unobserved heterogeneity only. So with the EM algorithm, I think it can be computationally expensive because you have to do the iterative procedure. And when you do each iteration, you have to estimate the utility flows of the payoffs. So this is why it's very useful in that paper that you exploit finite dependence, right? Because if you use finite dependence together with the representation lemma, then you don't have to repeatedly compute the in an infinite horizon decision problem. This infinite sum of the payoff flows, which is in contrast of a typical two-step estimation procedure where you typically have to do that only once, right? So that's why there is a lot of bias in the finite dependence assumption. So, but then one may not want to assume the finite dependence assumption. Of course, there are cases when it's natural to assume those assumptions when you have renewal choice, those kind of things. But in other applications, you're assuming that agents have finite memory of some sort, whether they're making training decisions or whatever. So those become real assumptions. And in some I/O applications, the finite dependence assumption is just, there's no obvious reason why it should hold. So in case you don't want to assume finite dependence assumption, then this is the direction that we are going to. And another potential issue with the EM algorithm approach when you move on to games is that when you iterate, your probabilities have to be model consistent, right? And then we know that in the dynamic game literature, when you have multiple equilibria, it's possible that there could be different probability profile. So you might get, absorbed into different probability profile which didn't generate the data generating that didn't generate the data, even if you assume that the data you observed came from a single equilibrium. So that's Astidiagono and Miller. And in terms of Kalupstides' work, so they assume that they have an instrument and then they set up a very nice, or I think cute way to estimate the pair of parameters through an Euler type equation. So they construct a moment condition using vectors and Michelsen's approach that you can get something that looks like an Euler equation in the dynamic degree choice framework. And they show that if we have an instrument, and again they assume finite dependence, then you can get a closed form estimator for the pair of parameters. So again, they assume assumptions that we may not want to assume. Moreover, the drawback of that approach is they only are able to estimate the pair of parameters. So this actually rules out you from doing the typical counterfactuals that empirical researchers may want to do, because you can't estimate the transition of the states, for example. Okay, so what we do then is we are going to work with large N and large T, because we want to estimate the transition distribution non-parametrically. So large T is necessary here unless you want to impose the kind of assumptions that Hu and Sham do, for example. And what we do, the idea is very simple, which is that we estimate CCP for every time period. We do K-mean clustering on that. So that would tell us what state or what hidden state of the world that we're in. And once we have that, then we can do the standard two-step estimation procedure. So, and there are many tools that one can use to do this, different ways that one wants to skin the cat. So I was taught this dynamic games model by Martin Pessendorfer. So I'm following their approach by taking this so-called asymptotic least squares approach, but a slight variation of what they do. So, in mostly dynamic games estimators, so Victor estimates his model using pseudo likelihood. Ariel uses method of moments, and Martin and Philip, they use this asymptotic least squares estimator, which is a class of minimum distance estimators with a weighting matrix. So with an appropriate choice of the weighting matrix, you can get Gabriel and Mirror's pseudo likelihood estimator when you don't iterate. And it can be shown that it is also equivalent to the GMM estimator also. And The feature of Pesendorfer and Schmidt-Dengler's estimator is that they essentially match the data-driven CCP and the model-implied CCP. So what we do is instead we match the implied value function, right? So which to me, at least from an econometric standpoint, is really the main distinction between Horst-Miller and Horst-Miller's Sanders-Smith. When you construct the GMM objective function. Yep. So that's the long introduction to the beginning of this, and but I think it's important to get these things across, and then I'll move on to the meat of this presentation. So the first part is quite econometrically, so I'll just try to give you the basic idea of what's going on here without going into too much detail by some notations. So yeah, so we are dealing with a discrete variables environment. So actions are discrete, observed states are discrete, the unobserved states are also discrete. So if you have repeated observation of this for agent denoted by n, and then we observe this over time, then at each time t, then you can estimate a choice probability that we denote by p hat capital NT, where capital N is the number of agents at each time period. So you assume a balanced panel, then n doesn't depend on t. Then we get an estimator of the true CCP, which is a random variable because it depends on dt that we don't see. Then we want to do k-means clustering on these observed or estimated CCPs. And the procedure of the k-mean clustering is that, given these estimated CCPs, you want to partition the data, or you want to partition your CCPs in L clusters with the objective to minimize the sum of squares within each cluster. Okay, so we want to do this. So Pollard has results in the 80s which show that if the random variable inside here, if you remove the hat and remove this capital N, suppose you have a times a sequence of random variables PT. So if you have ID variables PT, which come from a continuous distribution, Pollard show under very weak conditions that you can consistently estimate the cluster centers and derive, and he was able to derive asymptotic theory for these estimators. Of course, there's some caveats here because that the minimizer of this is only unique up to the relabeling of the cluster centers, right? So that's part of the difficulty in terms of how do you show consistency of this, but Pollard showed that. And yeah, then once you have consistency, Pollard then also show how you can also get asymptotic distribution as well. So for econometricians familiar with Pollard's work, then you know that this is going to involve empirical process theory, and then the objective function is going to be approximated by a nicer quadratic function where you can do where it's more visible where the asymptotic results comes from. So I think you shouldn't worry. Yeah. Oh, so I'm going to rule out non-stationarity area, but I'm going to allow for strictly stationary process. So essentially, the main difference in terms of the theory between what I'm doing here and Pollard's is that I'm clustering on dependent data whose distribution is changing with n. So it's kind of a k-means clustering of generated variables. Yeah, but I mean, I make it sound slightly more complicated than it is. Yeah. Sure.
Yes, the aggregate effect. Everybody, if I use the same aggregate effect, everybody has the stationary study that aggregate effect.
Yes.
So this is the aggregate effect.
Yes. Yeah, right. Yeah. Okay. Yep. So, I mean, then I'm not going to go through the details here, but essentially, to allow for us to apply the same analysis that Pollard went through is, we need to show that certain class of functions are Domesday, essentially. So when it's IID, it's straightforward. So here we need to assume that the mixing rate decay at a suitable rate that takes into the account of the complexity of the class of functions that we have to work with. So this just follow from Pollard in terms of the class of functions we work with, and then Andrews and Pollard, they have conditions on the mixing rate, which enable us to appeal to the Domesday theorem. So other than that, assumption A just say that conditioning on D, conditioning on D, the agents are IID. Okay, and then across time, we have a strictly stationary and an alpha mixing process. Oh, so F is the class of functions that we need to be P-Domesday. So this comes from when this F. Yeah. So it comes from, it's easier to see from here. So no. It comes from when you do K-means clustering on this, and you would, to get the theory, you need to do a quadratic approximation of this thing. So you do a tailored expansion around this. So it's the remainder term that has to be P Domesday. So that's the class of functions that the remainder term from this approximation. So when you do tailored expansion of this around the true, let's say, right, the remainder term, I mean, if we don't have this minimum, then it's a trivial problem. But because, it's a K-means clustering problem, then, this remainder term can be jumpy if you look at, like, say, P near the boundaries of the center of the cluster, for example.
This like a function, like in a sense, it's like a finite dimensional problem. Like all the state variables finite. So it's not really a function itself, just like a set of premises.
Well, it's almost parametric, but then in our case, but in our case, it's a little bit more complicated because the distribution of our p hat, although it's a discrete random variable, but the support of it is going to infinity as n goes to infinity, right? Because if you think of p hat as a frequency estimator, the number of the support is going to infinity as n goes to infinity, right? It's an estimator of the conditional probability. Yeah. So I mean, it's yeah. So I think it's a little bit, well, it's, to me, it's easier expose having seen what we need to do, but yeah, I mean, I'll try to point this out. Okay, so I'm a little bit short of time. So yeah, so the other key assumption, other than the technical assumption, is that we need the class of center to be well separated. Okay, so we need this, and then we need them to stay away from the interior, boundaries of the parameter space. Then so that deals with the dependent structure of the K-mean clustering problem. So to deal with the fact that we have a discrete random variable as opposed to a continuous random variable like Pollard. So in Pollard's work, if you have a random variable drawn from a continuous distribution, then the remainder terms, the main concern there is really what's going on at the boundaries of these clusters. So, they either they have zero measure, for example, but in terms of the asymptotic theory, you need to integrate over this region. So there's something to do there. So in our case, given that we have a discrete random variable with support size increasing, what is working for us, at least to make the theory work, is that if our CCP is consistent at every time period, although the support is increasing in cardinality, the concentration of the probability is going to be centered around the true CCPs, I mean, the true probabilities, right? So essentially, assumption B is saying that if our estimator of the CCP takes its form, which means that depending on what its true unobserved state is, we can consistently estimate the true cluster center. And then we have a stochastic component, which is, the asymptotic normal part. and some remainder term that satisfy this condition. So these conditions, again, I mean, the point is we just need to have these things holding uniformly, because what we need to be able to do is to say that, you know, if you put, you know, a ball around all these cluster centers, then with large probability, the estimated CCPs would be in the right in the right centers. That's what we need to do. Once you can do that, then you can ignore all these boundary issues that Pollard has to use the density of the distribution to deal with. Okay, so this is why we need these conditions. So the nice thing, though, is that under assumption A, the frequency estimator, and as we expect other estimator you may want to use in this context, would satisfy assumption B. So it may look like there are a lot of things going on, but it's actually pretty weak in our setup. So yeah, I'm not going to spend time on this, but you know, so if you assume all of this, then as long as n grows faster than log t, then we have an asymptotic distribution for cluster estimator. So p hat n is a particular label of the cluster estimator, the cluster center estimator, and p0n is the minimizer of the expectation counterpart of the objective function. Yeah. Because you mean the P0 or this one? Yeah, so this is because if you look at the objective function, right? Our estimated CCPs, they depend on n. No. Yeah, so it's the same setup at Kalup Studio where, you know, you in each time period, say in a single market, right? You have many agents making decisions, but their decisions separated from the macro effect. So, you know, although you have many of these guys making decisions and you're observing more of them, but they don't influence.
So I'm not, I think, I'm wondering whether there's a simpler way to do it, and they will help them.
I see. Yeah, I haven't. Yeah, I need to think more about that. Yeah. So yeah. So given this, then you know you have so you know given these assumptions, essentially what this result says is that we can get the same kind of results that Pollard has when the data is sampled from an IID case with continuous distribution. Okay, so I mean this is just saying that you know this objective function can be approximated by something that looks like a quadratic function where the asymptotic theory of the estimator would come from the minimizer of this, right, which would be this thing here. So this is typical Pollard type argument when you do a quadratic approximation of the objective function. So P naught and P naught n. Yeah, so P naught n is the minimizer of the expectation of this. Yeah, and then P naught would be the case when you replace this by PT, which is a trivial clustering exercise, right? Because in that case, if we know the true CCP here, because everything is discrete, the true PT is a discrete random variable. So if you observe the true PT, then clustering here is trivial. I mean, as soon as you know you observe L different ones, then you know exactly what are the L centers. Anyway, so once you have this, then you can also estimate the unobserved DT too. Then you know I'm gonna gloss through this quickly because I want to get to the other parts. Yeah, then you know then you can just estimate this thing by the sample counterpart of these probabilities, and then you use D hat instead of D or instead of D, right? And then we show that under assumptions A and B, as n and t goes to infinity, and n grows at a faster rate than log t, then we have consistent estimator of these probabilities. And similar to Bonhomme and Manresa, we also can show that if n grows at a faster rate than square root of t, our estimator of these objects by using d hat instead of the true d, we actually have the same asymptotic distribution. So lemma 4 shows that the difference between the estimated, the feasible estimator of these probabilities, which I stack together in a vector here. So lambda hat m, for example, is the vector of marginal probabilities, and lambda hat j is a vector of estimated joint probabilities, and with the suffix c, it's a conditional probability. So it's the sample counterparts of these things, right? When you use d hat to estimate it, and then the lambda tilde is the infeasible counterpart, where you use the unobserved dt. So we're just showing here that this difference is going to be little op 1 over square root of t, which means that in a large t asymptotics, the asymptotic distribution of lambda hat m, lambda hat whatever, is going to be the same as the asymptotic distribution of these guys, because we know, they converge at the root t rate. Yes, Dennis. No, I thought you're going to say something. Okay. Yeah. So these results then tell us that we can consistently estimate, these unobserved states, and we can consistently estimate their transition probabilities. Then we can go to the Markov decision process, which would look more familiar to what was covered in the summer school. Then we would make some assumptions on the DGP here. So for the last part, it's just an incorporation of this unobserved D, really. Okay, so the first assumption says that the utility function is additive separable into the part where the payoff depends on the action observed state and the unobserved state D, which is time varying. And then there is the epsilon term that enters additively. And we assume that this pi function has a linear in parameter specification. So the linear in parameter specification is not necessary for our asymptotic theory, going forward, but it just facilitates estimation. Yet at the same time, it's not all that restrictive, because A, X, and D are all finite. They have finite support, right? So this assumption can be seen as a non-parametric one. And you can think that, when the normalizations or whatever restrictions that you impose are non-parametric. Okay, so yeah, then the transition law, if you don't have the D's, then this is the standard conditional independence assumption. Of course, we can also allow for this distribution of epsilon to depend on X, okay, but we rule that out for simplicity. So with D, then we have this macro effect where, well, I should not use macro effect because I know Ariel is not happy with this, but yes, so this and DT just evolved exogenously from the other component of the model, although it affects what decisions the agent would make at each time period. Okay, then epsilon has some known distribution that you can assume to be normal, extreme value, whatever. And the discount factor is assumed to be known. Again, for simplicity, if you want to estimate this, it's fine. I mean, it can be shown that under different conditions, this can be identified. So in this setting, then the parameters of the model are theta, beta, and f. We essentially assume that we know beta. We assume that we know much of f, and we can consistently estimate the remaining part of f, so we know that as well. So what's left to do in terms of inference is to estimate theta. So so I have a couple of slides which kind of give the basic idea of asymptotic least squares in case it's not, I think it's for sure less familiar to most than GMM or pseudo or like likelihood-based estimation, but I think I'm a bit short on time. So I just want to say that basically, when you have a finite, when you have conditional probabilities, you can forget about the unobserved heterogeneity for now. So when you have a CCP on finite states, then you can non-parametrically estimate the CCPs as a finite dimensional vector, right? So you can estimate that non-parametrically using, say, the frequency estimator. And then you have the model implied version, which depends on theta, through, where this probability would have to take into account the fact that this probability is calculated from you taking the optimal action or the optimal choice with respect to a particular parameter theta. Then the asymptotic least squares estimator is just simply matching, these two vectors as closely as possible by choosing the theta that does that. So that's the asymptotic least squares estimator. And, depending on the choice of the weighting function, then you get different asymptotic variance, which affects the quality of the estimator. So what we do instead, so this is what Pessendorfer and Schmidt-Denkler proposed in their paper. So what we do is, instead of minimizing the distance between the CCPs, the estimated version non-parametrically and parametrically, we compare the difference or the distance between implied valuation of the flow utility instead, right? So we know from Hodge-Miller's inversion, these are one-to-one mapping between the two. So we do that. And the reason we do that is because we can exploit when theta enters a pair function linearly, right? So this also has been exploited in other estimation procedure also. So when that happens, this V theta can then be written as, some linear combination of theta. So this least squares problem, this asymptotic least squares problem has a closed form solution, right? So, if I replace V theta by capital X theta, as long as I can invert this matrix, I get a GLS type estimator out of it.
This is sort of the shoe that this extra state variability. It doesn't include the utility functions. It's more like this.
It does. It enters through this. Yeah. Yeah. So I also want to comment. So in terms of identification, So V would be the differences between the expected utility that you get, say, from choosing certain actions, say, in a two action case, would be the difference between the expected utility from choosing action 1 versus action 0 when you, that's roughly what you get from that, right? So you're gonna get like infinite sum of these guys with some expectation and discounting on them. So it's a linear function of theta. So you get this. So So this example came from a static case. So there's no dynamics here. But anyway, so the point is we can get a closed form estimator just like Kalupstidi and Scott and this guy. So they have a type of IV expression, but we have an OLS GLS type expression. So the point is the model would give us something like this. And Y and X are functions, are known functions of beta, pi, Q, H, and G, which we either know or we can estimate non-parametrically. So under the full rank condition, which is the high-level identification assumption here, we can invert this guy. So then if we have consistent estimator for these things, then we just plug them in, right? And then we have a closed form estimator here. And then the asymptotic property of these asymptotic least squares estimators really come from the estimator of H and G, right? So here we have large N, I'm going a bit faster. So large N and large T framework. So the only variation that we're going to get asymptotically is going to come from the estimator of H, because the estimator of every other component would converge faster than the rate of 1 over square root of T, because they have N anti components. Okay. So perhaps more interesting is how does this work in practice? So this is a very is a fairly simple game, but we go to Pesendorfer and Schmidt-Dengler's dynamic entry game with 2 players. So this is exactly the same setup as Martin and Philip have, with the only difference is that we have this unobserved heterogeneity here. So we were setting up the kind of simulations in this particular way, and of course you have to assume something about this omega because otherwise you cannot identify them. So we assume that the omega are decreasing or increasing depending which way you go. And then omega 1 is set to 0. So we only have the simulation results when L is 2 at the moment, but we are doing others, of course. And these are just some parameters. So these are the same parameters that Martin and Philip use. And of course, other than the addition of these omegas. And so before I show you the results, these are the equilibria. So in the original model without unobserved heterogeneity, there are only 3 different types of equilibria: the unique, the symmetric one, and 2 others. So with this unobserved heterogeneity, we have another equilibrium. So the observed state here is a past action of player 1, player 2, and here is the column for D. Okay, so I list this in this particular way is so that you can see that when D switch from 0 to 1, what do CCPs look like? And we also have here the distance between this vector, the vector in the lower half column and the top half column. So this gives us a sense of how well separated the cluster centers are. So in equilibrium 1 and the symmetric equilibrium, the separation are relatively small compared to equilibria 2 and 3. So when we go to the results, so we do this for different, should be N here, different N and T. And, so there are a lot of numbers here, but roughly speaking, if we look at the mean square error, so this is the mean square error multiplied by 100, otherwise the numbers are too small. Okay, so so when you have more observations in either direction, things improve, things improve for the infeasible and the feasible estimator. The naive estimator just ignores unobserved heterogeneity completely. So if we do that, of course, you're going to get an inconsistent estimator. But otherwise, things work pretty well. The bias is small, and the standard deviation goes to 0 as it should. And this column here, detects the proportion of D that we predicted wrongly based on the model. So in the symmetric equilibrium, this is what we get. We get a very similar picture for equilibrium 1. So if you focus on the MSD column or even the D bias column, but when you move to equilibria 2 and 3, when we know that the probabilities are well separated, then you see that the percentage of correctly predicting D is very high. In that case, the infeasible and the feasible estimator are almost identical, right? So this is what is predicted by our theoretical results asymptotically. So yet things seem to work well in this very simple setup, but of course we need to look at a more general setting. And I know I'm out of time, so I just spend yes. Which part, sorry, Eric? Oh, before this. No?
So let me just say, okay, the difference between the comparison is there is an aggregate shock, but it only affects the exit. So they end up on a station. You're doing is you're putting it outside. That's a useful thing you should get around. And it's particular modulus of getting itself. But the place where it's really likely to be really useful for IO is in transportation. Because they're going to a set a unique steady state. Whereas in your model, you're allowed to aggregate effects like run to the war in the Ukraine, and that would change everything. Your model depends on whereas there so that's just
Right. Yeah, no. Thanks. Yeah, so I think in this case, we can somewhat incorporate other observed time varying factors also. I mean, to some further identifying assumptions. Yeah. Okay, great. Yeah, thank you. Yep. So 15 seconds are real. Yes. So so basically I've done all these things, but what I'm trying to say is that, so this idea is a very direct approach to dealing with the time varying unobserved heterogeneity. And I also believe that it's directly extendable in other kind of games. You have order action games. Or, if you want to allow for some continuous variables, you can also look at continuous action game under the kind of like super modular type utility function. We can the idea works too in general, but I think the theory, at least for the econometric theory for this case, would be more difficult. But otherwise, the basic idea should apply. Okay, thanks. Sorry for overrunning.